All right. So have your trig chart out at the ready. We are going to be a whirlwind this morning of new formulas. All right. So we're going to start working our way through the rest of that trig chart. So 7-1A, basic trig identities. So the first thing that we need to remember are the circular function definitions. We're going to be using these. So sine, cosine, tangent. Circular function definitions, if you remember, that was your trig functions no longer in terms of opposite, adjacent, and hypotenuse, but instead x, y's, and r's. Does anybody remember what was sine?
Y over.
Yeah, sine was y over r. The generic picture that we have for that was for an angle that's rotated up there at a given theta. It's going to have x coordinate and y coordinate and be a distance r away from the origin. Now, obviously, this could go into any quadrant. Cosine, what was cosine?
X over.
X over r. Tangent? Y over x. And then we had the cosecant, secant, and cotangent. So cosecant theta, secant theta, and cotangent theta. And this is based on our understanding that cosecant is the reciprocal of sine. Secant is the reciprocal of cosine. Cotangent is the reciprocal of tangent. So these circular function definitions were simply the reciprocal of sine, cosine, tangent. So cosecant was r over y, secant, and cotangent. Question, do y'all remember talking about all those things? Seeing some head nods, not falling asleep, so that's good. All right, so one of the things that we also discussed very briefly was something called the tangent and the cotangent identities. And what that said is, we found out that tangent of theta, which could be written as y over x, we could modify this slightly if we multiplied the numerator by 1 over r and the denominator by 1 over r. Now, of course, anything over itself is equal to, not 0, 1. So 1 over r divided by 1 over r, that's the same thing as 1. And when you multiply anything by 1, are you really changing its value? No, you're just changing the way that it looks. So this is y over r divided by x over r. And if you recall, hey, y over r, I've seen that before. What's y over r?
Sine.
Yeah, that's the circular function definition for sine. So sine theta, actually. And x over r, hey, I know that. That's the circular function definition for cosine. So it turns out that tangent of theta can be written as sine theta over cosine theta. And for that matter, cotangent, which is simply its reciprocal, cosine over sine. Okay, so this is a way that we developed some new formulas, well, they're not technically formulas, they're called identities, because whatever's on the left-hand side is equal to the right-hand side. there are some more identities that we're going to discover. And here's the first one. It's called the Pythagorean identity. And when you're discovering identities, we really don't have an equal sign. We just start off with something complicated. So sine squared, actually, I'll show you something. Sine of theta squared plus cosine of theta squared. So the whole thing squared. Mathematicians, we really don't like to write those parentheses if we can avoid it. So we're going to write that as sine squared theta plus cosine squared theta. We put the square in between the trig name and the angle. Have y'all ever seen that before? Never seen it? Just as a little side note, there's what we're talking about, sine of theta squared. That is not the same thing as sine of theta squared. Okay? For instance, this would be like, this over here is like the sine of 30 degrees squared. Since y'all have your trig chart out, what's the sine of 30 degrees? This little note. 1/2. So 1/2 squared, it means what we're squaring is the actual result of taking the sine of that angle. So 1/2 squared is, anybody?
1/4.
1/4. What this over here means is the sine of theta squared, which would be the sine of 30 squared. Or in other words, the sine of, what's 30 times 30? 900. So the sine of 900 degrees. Somebody with a calculator. Why don't you have a calculator? Grab a calculator. Everybody grab a calculator. Always have a calculator. Let's go. Wasting screen time. Matthew, what's the sine of 900? Degree mode.
Sine 0.998.
3 nines and an 8? No.
2 9s and 8.
2 nines and an 8. Okay. Well, now we've gone through and chased this this rabbit here. Are y'all in agreement that 1/4 is not the same as 0.9998 or 0.998? I would agree with you on that. Do you see the difference between the square here and the square here? Gabrielle, does that make sense? Square there, square there.
Never
So-
mind, I had it in radians.
You had it in radians. So
Yeah, it's 0.
it's 0. Okay. Well, that's even more not equal, if that's possible. Okay? So when we have a sine and we put the square right there, what we're meaning is the sine of theta, the whole thing, squared. That's why you got that? Alright. So, now we're going to break this down and see what it equals. Actually, kind of interesting. So, sine squared of theta, we will return everything, if we need to, all the way back to these, the circular function definitions. So what is sine? Y over r. So we've got y over r squared plus x over r squared. So y over r plus x over r. So that would be y squared over r squared plus, that's why you shouldn't use a calculator for this, it's just some of this here. X squared over r squared. We have a common denominator, so we can write y squared plus x squared all over r squared. Now at this point, it's helpful for us to recall what x and y refer to. So we'll go back to this picture. X and y are the two sides. If you want to think of it in terms of vectors, they're the x component and the y component. Okay? The two parts of that angle, the x part and the y part. So here's a question. What is y squared plus x squared?
R squared.
R squared. How do you know that?
Pythagorean
Yeah,
theorem.
Pythagorean theorem, hence the name. Identity. Now, normally we're not used to seeing the y first, we're seeing x squared plus y squared. But, would you all agree with that?
Mhm.
So, y squared plus plus x squared rather is r squared. So we can replace that with r squared over r squared. And it is 1. Which leads us to our first identity, that is that sine squared theta plus cosine squared theta equals 1. Alright, let's do another one. 1 plus tangent squared theta. So what do we say that tangent is represented by? We could put it as sine over cosine. We could put it as y over x. We'll return all of these to the x's, y's, and r's. So y over x. So 1 plus y squared over x squared. I want to combine these two terms here, but I don't have a common denominator, so I'm going to rewrite the 1 as x squared over x squared. So now I can combine them. I have in the numerator x squared plus y squared, and in the denominator I have x squared. Well, hey, what's x squared plus y squared? R squared. So r squared over x squared. I'm going to rewrite that as r over x quantity squared. Look familiar?
That's, wait, no, that's why.
You're almost there. It's not cosecant.
It's secant.
It's secant. So this is secant of theta squared, or we would write that using our new terminology, secant squared theta. And that's the way that we say it, secant squared theta. So that's our second Pythagorean identity. I'll write it over here. 1 plus tangent squared of theta is equal to secant squared theta. Matthew, peek on that iPad, make sure that the clock's still reading.
It's still going.
Can you see me?
No, but I can see what you're writing.
You can see it right? That's all I need to see.
Alright, now you can see.
Alright. Well, you don't, I'm not important. The material is important. I'm just a bonus. Alright, let's see if we can do a similar thing with cotangent, and we'll change the color here. So 1 plus cotangent, it's going to follow this almost exactly. 1 plus, let's rewrite cotangent. Back in r's, y's, and x's. What's cotangent called out?
X over y.
X over y squared. So we have 1 plus x squared over y squared. You can probably see where we're going with this. Rewrite the 1. So y squared over y squared plus x squared over y squared. That's going to be y squared plus x squared all over y squared. What's y squared plus x squared?
Y squared.
R squared, yeah.
Oh, yeah. No, right.
So r squared over y squared, we could rewrite that as r over y quantity squared. R over y, why that happens to be cosecant. So this is cosecant squared of theta. And our final Pythagorean theorem, 1 plus cotangent squared, sorry, Pythagorean identity. 1 plus cotangent squared, cosecant squared theta. The first one is kind of unique and unto its own. The second and the third, you can definitely see the resemblance, 1 plus, and then you've got the tangent, cotangent, secant, cosecant. So when you have these memorized for your memorization quiz, you can have little tricks to help you remember those things. Anybody have a question about Pythagorean identities? Alright, let's move on to some more identities. But for these, we're going to draw some graphs. First off, draw a good old sine graph. In fact, we're going to draw it right here in the middle. We've got a lot of experience with sine graphs. So we know that it starts at the baseline, ends at the baseline at 2 pi, in the middle it hits pi. Y'all are probably tired of hearing me say that. Thought we were finished with graphs. We pretty much are, but we're going to use our knowledge of graphs to help us generate this next set of rules. What I want to do is I want to see what happens in the negative territory. So y'all can probably imagine, you've seen it before, it just does the same thing like that. We've got negative 2 pi, negative pi, negative pi over 2, negative 3 pi over 2. So what we want to come up with is some sort of rule for relating the positive x values to the negative x values. So let's compare sine of pi over 2. So what's the sine of pi over 2, folks? 1. Sine of pi over 2 is going to be 1. And over here, let's compare that with sine of negative pi over 2.
Negative 1.
Negative 1. So we would say sine of pi over 2 equals negative sine of negative pi over 2. What about the sine of 3 pi over 2 versus the sine of negative 3 pi over 2? What's the sine of 3 pi over 2? Somebody?
Negative 1.
Okay. Somebody else? What's the sine of negative 3 pi over 2? Positive 1. So the question is, would you agree with this statement if I say are they exactly equal? No. But what if I put a negative right there? Is negative 1 equal to negative 1?
Mm-hmm.
Yeah. Sort of like 1 is equal to negative 1. So. And I guess we could try another one here just for good measure. Sine of 2 pi versus sine of negative 2 pi. What's the sine of 2 pi?
0.
Sine of negative 2 pi?
0.
So would this statement right here still be accurate if I put a negative right there? Because is 0 equal to negative 1 times 0?
Mm-hmm.
Yeah. So let's make a general formula here. The sine of, I think we're going to put x in this case, is equal to negative sine of negative x. Cammy, does that make sense? Just based off that pattern. Is it true absolutely every single place? Well, I mean, look here. If I just pick some point, that value here, if I go some small distance, I don't know, c. If I go this same distance, negative c, look, it's gonna be that same value, whatever that height is, but it's gonna be negative. Y'all with me on this? Okay. Make sure. That's a formula, but we really don't tend to write it that way. We tend to take this just 2 steps further. We say, all right, okay, great, that's all well and good. What if I have a negative here? What if I make this negative? Sine of negative x. All right, negative sine. So I'm plugging in negative x right there. So when I plug that into this formula, I would have negative x. Why would you do that? The reason is for something that you'll see really in a minute. Okay? So just plugging in negative x there means up here where I had just regular x, I'm going to plug in negative x, so I have negative x. So this is the final formula that we get. Sine of negative x is equal to negative the sine of x. What good does that do? Well, if you have any angle that you're calculating the negative, say sine of negative 30 degrees, that's just negative sine of positive 30 degrees. We can use the trig chart real quickly, use our unit circle to figure out what this is. Does that make sense? So if you have a negative angle right there, then just say, all right, well, I'm going to find the sine of the positive angle equivalent, but then stick a negative in front of it. So sine of 30 degrees, and we say that was 1/2.
Mm-hmm.
So the sine of negative 30 degrees is just going to be negative 1/2. It's just a quick way of doing that. Okay. Now something similar with cosine. So go ahead and draw your cosine graph. So my question is, do y'all think this is going to have the same type of thing as sine, or is it going to be different?
It's
It's gonna be different.
Why do you think it's going to be different?
Because-
Yeah, because he's saying is the negative are starting off positive and here's positive. Katie, why do you think it's going to be a little bit different than sine?
Because sine was basically like, the negative was just like flipped from the positive side, and this is basically the same thing. It's like a mirror image.
Exactly, it's like a mirror image. This process should go a whole lot faster. So let's compare cosine of pi versus cosine of negative pi. So cosine of pi, it happens to be -1. What's cosine of negative pi?
-1.
-1. Guess what? They're equal. What about the cosine of 2 pi versus the cosine of -2 pi? 1. Cosine -2 pi? 1. They're equal. Do we need to keep going? You're all pretty convinced. The rule here is that the cosine of -x equals the cosine of x. So to use our 30-degree example, the cosine of -30 degrees is simply equal to the cosine of 30 degrees. So these are just some tips and tricks, and actually you can find these on your trig chart.
Oh, right there.
These are called the reduction formulas. I guess I should have put the name there. Reduction formulas. Are they reduction? Yeah. And you can see that just for the sake of time, we are not going to go through the same process with secant, cosecant, tangent, and cotangent, but you can look and see, you can get pretty much the idea of what's going on with those. All right. Now the cofunction identities. So this is one of the last times we're going to do graphs, I promise. So don't worry, simple graphs, sine, and then directly beneath it, cosine. So we're like total experts at this. Now the trick is you want to kind of draw some vertical lines here so that we can match everything up. Okay, so start high, end high, middle low. So there's sine of x, here's cosine of x. So we're going to finally answer this question that we've been talking about all semester long, well, all the last 3 weeks long we've been doing graphs. Doesn't sine look an awful lot like cosine? Yeah. In fact, if we were at sine, how could we manipulate it to get to cosine? How can we make that sine graph look like the cosine graph?
Move it.
Shift it left or right. Yeah, it doesn't really matter, but for simplicity's sake, we're going to shift it to the left. Okay? So that means it's going to have an x, and then what kind of a symbol right here? Plus.
Or, no, pi.
Half pi? Let's see here. Well, I'm thinking,
Yeah, it'd be half pi.
so if I shift that there, then I'm going to end up here. That's right. Yeah, pi over 2, which you were right, half pi. If I take this point right here, oh, sorry. This point right here is shifted. Yeah, everything's being shifted to the left. Pi over 2. That's the simple way of, that's where we're going to get started. If you look, though, at your trig chart, it doesn't have that. That is a true statement, and that is very helpful. Okay, that is one of the forms of the cofunction identities. But this is the way that a lot of textbooks and a lot of the formulas work out. Let's change this up a little bit. We know that this is true. I'm going to plug in negative x. So instead of x here, I'm just going to plug in negative x. But that's no big deal because I know that every time I see negative x, I'm just going to plug in negative x. So I'm going to have cosine of negative x. Then I'm going to rewrite this in a way because I don't like anything negative out front. So the sine of pi over 2 minus x equals, and now you're like, now I know why you did those reducing formulas. The cosine of negative x, we found out that that is equal to just cosine of x. And
Why
that,
is x negative?
well, I can plug in a negative number if I want there.
Oh.
So if I choose to plug in a negative number, then I've got to plug in the same negative number over here.
Okay.
I'm plugging in a negative x to show this, which is the way that most formulas are going to read it. I prefer this way personally because it's very easy to see that there's a shift. Okay, but whatever. In the same way, so I'll say dot 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 you've got cosine of pi over 2 minus x equals sine x. So maybe that explains why they work like that. I think we probably need to look at that one. Your immediate thought is, wait a second, that's really pretty, right? Look at that. Sine of pi over 2 minus x equals cosine. Cosine of pi over 2 minus x equals sine. Something doesn't feel right there. You know what I mean? Every other time we've had sines and cosines, this looks different. So let's just take 1 minute here, maybe 2. Let's look and see how they got that second one. Well, we're going to have to draw another graph. First one we're gonna draw one on top of the other here like this.
Well, since they're basically both the same graphs, if you shift one way, it'll be equal to the other one.
Yeah, except that would normally you would expect like cosine plus pi over 2, and that or cosine minus pi over 2, and that's not what we have here. Okay, you want to try that? Let's try it. Sure, we'll try it. So you can say, if you start off at cosine right here, what is it going to take to get to sine? And the answer is, well, you shift it over to the right. Okay, sure, we'll try it.
X minus pi over 2.
Sure, x minus pi over 2. That's going to equal sine x. Okay, but I need to try to get this to look like that. So, really, I mean, if this is true, what if, well, see, you've got to negate that, and then you, because I want this to be a plus.
But isn't it true though?
Yes, that is absolutely true. Cosine of x minus pi over 2 is going to equal sine of x. Show you real briefly though how you can get at this, how you get to that equation, and it involves a little bit of a weird thing. Drawing the negative cosine graph. Starts down here. Negative cosine x. And comparing that with the sine graph. So that's true.
So to get the bottom one over here, it'd have to be a negative cosine graph. No.
Well, if we do, well,
Because
watch it. If you start off with that negative cosine, and if you want to shift everything to the left, you see that?
Yeah.
Shift this to the left, you get right up here. Shift this to the left, you get right there. Shift this to the left, you get right there. So negative cosine of x, we're shifting to the left, so we put plus pi over 2. That's going to give you the sine of x. And then we do the same kind of trick. We say negative cosine, and I've substituted a negative x right there. Negative x plus pi over 2 equals sine of negative x. You have negative cosine. I'm going to rearrange those. Pi over 2 minus x equals, what's, now using our reducing formula, what is the sine of negative x? Jesus, set up please.
Negative sine x.
Negative sine of x. Negative and a negative, you can divide both sides by a negative 1, cancels. And so you have
The original
cosine, yeah, pi over 2 minus x equals sine of x. I don't know off the top of my head how to get from here to here. Okay? So I can't necessarily, there is a way, I'm sure mathematically you can get there, but you can't just switch them, and you can't just put a negative in front of there. So you've got to do something, there's something else that you've got to do I can't just think of. But I know that if you start off with the negative cosine, then you can see graphically that negative cosine, x plus pi over 2, so shift it to the left, is going to give you sine. Substitute in negative x, you can arrive at this. So it feels, I mean, it's really nice. And the OCD part of me is like, this is great, you know? It's just the same thing. I don't have to memorize as much, okay? It's just blah, pi over 2 minus x equals the other thing. In fact, it's the sine of this is equal to cosine. Cosine is equal to the sine. And in fact, if you look there on your chart, you've got the secant of pi over 2 minus x equals cosecant.
Oh, it's basically the same thing.
Yeah, the tangent of pi over 2 minus x equals cotangent, which is why these are everything is matched with its co-function, its counterpart. Yeah. So that's why these are called the co-function identities. And they all look beautiful if you have pi over 2 minus x, because they all match the same way. Otherwise, you're going to have sometimes x plus pi over 2 equals negative and stuff like that. So it really works out really, really great if you do it that way. Okay? Believe it or not, that's all the formulas for today.
Oh, just for today.
So for today, well, we're gonna continue. We're gonna work all the way the rest through that trig chart. You know, you've got to learn all of these. But let's go ahead and do a couple of quick problems together. This is one of those cases where the problems are actually a lot easier and a lot shorter than any of this stuff. Next one there, handy. All right, so this is what we call a 2-for-1. You get two
Oh, look at that.
papers on one sheet of paper.
Oh, so it's homework and notes.
Don't forget notes, because that's how simple this is.
It'd be a lot easier.
There are, in fact, several ways that we could solve these problems. First one says, find cosine of theta if cotangent of theta is 4 over 3. Okay, well, one way that we could do
Wouldn't
this problem.
it just be 4?
What's that?
Wouldn't it be 4 if it cotangent is cosine theta over sine theta?
Because it's
Wouldn't cotangent theta, since you've got cosine over sine, wouldn't it just be 4?
Yeah, and then sine would be 3.
I don't know, that seems a little sketchy. Let's reduce it to x, y's, and r's and see if you're right.
Alright.
So cosine of theta is, in terms of x, y's, and r's, it's x over r. What is cotangent?
X over Y.
X over y. Okay. So we have, if we were to draw a picture of this, we have x, which is 4, y, which is 3. Hey, I know that triangle. It's a
3, 4, 5.
3, 4, 5 triangle. So cosine of theta is, yeah, x over r, so that's great. So this is our x. This
Oh,
is our
okay,
y.
so
this is our R. So it's going to be 4 over 5. What if I didn't know this special Pythagorean triple?
You'd have to do Pythagorean.
You'd have to do Pythagorean theorem. Yeah, it's really not that bad. Okay, 4 over 5. Why is it not just 4, like Matthew said, super shortcut?
Well, isn't it, never mind. I was going to say that.
Well, let me show you. The thing is that this is a reduced version of the answer. Because we just found out that cosine is in reality, it's 4 over 5. What's sine?
3 over 5.
3 over 5.
That's like with the y over r over x over r.
Yeah.
Or something like that.
Okay? So, 4 over 5 or 3 over 5, if you think about that, that will reduce. 4 over 5 divided by, so multiplied by the reciprocal, 5 over 3, it reduces to 4 over 3. So it's just,
Okay.
it's the simplified version. So you may be tempted to take the Matthew shortcut, but not all shortcuts take you to where you want to go. All right. Let's look at.
So the answer is 4 though, right?
No, the answer is not 4. The
It's
answer
4 over 5.
is 4 over 5. Yeah, that is. The only reason why 4 appeared to be the answer is because cotangent is cosine over sine. But when you put cosine over sine, it actually reduces to 4 over 5.
Okay.
So this is a reduced form of the answer. Okay. Let's pick another one. Find cosecant theta if tangent of theta is 7 over 24. Well, what's cosecant?
R over y.
R over y. What's tangent?
Y over x.
Y over x. So my y is not the scale, obviously, is 7. My x is 24. Uh-oh, I don't have that one memorized. Maybe you do. It's actually one of my favorite Pythagorean triples. 25 here for my r, using Pythagorean theorem. So cosecant, since it's r over y, is going to be 25 over 7. All right. There are lots of ways. Those last couple will give you a little bit of a challenge. We're reminding you of your radical equations. Just as a reminder, today we talked about, call them out, class. Basic trig identities. Okay, yeah, let's be more specific about which basic co-function identities. Pythagorean identities and yeah, the reduction formulas. I don't know why they call those formulas. I call them reduction identities. But anyway, there you go. On the back is the homework. So a little bit of a bonus there.